Hello everyone, my name is Mitchell Spencer and today I'll be talking to you about the line following rover that I built. So just as an overview, I wanted to design a rover that would trace an arbitrary line on the floor. This means that we would have to have sensors to sense where the line is and how the line turns, and appropriately have motor responses that steer the rover accordingly. So this is kind of a wide-ranging project that is very popular in general mechatronics classes and applications. Some of those applications include just general automated equipment carrying. This is kind of what you would see at like the Amazon warehouses with those robots that carry things back and forth, and then also extensions to higher problems. So through the solving of this problem, we could maybe branch off to implementing things like magnetic sensors or something as general as a self-driving car, whereas instead of following a line, you'd be staying in between lines. So very similar in application. So to go over the hardware that I used for this project, ultimately, just because of the scope of the project, I didn't want to spend a lot of time trying to develop any sort of PCB board. And so after talking to Trudy, we both decided that ultimately it would just be appropriate to incorporate the entire EasyPick Pro development board as part of the chassis. So it ends up being quite a large robot. It looks kind of silly when it works, but this is just what ended up having to be used for this project. So we have the entire development board on the chassis. We also have these 3 infrared reflective sensors, which I'll go into a little bit more depth later, but they basically are what are looking at the line on the table. We also have the motor driver, which routes signals from the pick to the different motors, and also incorporates the 2 battery packs up here that are used for it. Then we have the 2 DC motors as well. These are what steer the entire chassis. And then also in the back, there is a kind of a rubber stopper on the bottom that just gets dragged around. So, and then let's keep going. We've got the 9 volts to power the pick board itself. And then we also have 2 AAA battery packs that contain 3 AAA batteries. And so with each battery containing 1.5 volts, that's a total of 9 volts or 4.5 volts per motor, which is within the recommended tolerances for both the motors and the motor driver. So as a summary of the software, I've developed a C program which takes in ADC signals from the infrared sensors and then uses software logic to output high and low signals to the motor driver. And then there's also a PWM output, which required the utilization of the PWM feature within CCP. And that's from CCP4, that's multiplexed to RG3. So that's, I used the signal from that pin directly input into the motor driver as well. So there are certain parameters that can be used to tune the performance of the rover. So there's the sensor sensitivity, which ended up being kind of finicky, but ultimately there's an actual potentiometer on each of the sensors. It's really small, but you can turn that to adjust the sensitivity so that if it's not detecting the line, or if it thinks it's detecting a line when it isn't, you can twist that and kind of make sure that it's within the right range such that when it is over the line, it's showing that it's actually over the line. And then the last thing is the motor speed, kind of like what I was mentioning with the PWM output. The duty cycle of the actual PWM signal dictates the speed of the motors individually. And while you can't have individual PWM signals, I chose to make them both equal. That could be something that could be explored in further developments or other reproductions of this project. But for now, I just decided to keep them both at the same PWM signal. A general overview of how it works. So here are the infrared sensors. You can see the potentiometer on the top actually that can be used to adjust their sensitivity. And on the bottom, you see there are 2 little bulbs that are separated by a wall. One bulb casts infrared light and the other receives it. So if it's over this reflective tape, then it will alert the pick, and that's ultimately what is determined. That is ultimately what the software logic goes off of to direct the rover to turn or to drive straight. So we have this table, which is provided from the motor driver data sheet. And ultimately, this shows that the input signals into the motor driver and how they affect the output signals, turns out they're actually perfectly mirrored depending on which direction that you want to go. So ultimately, by changing the signal for one of them to be on and one of them to be off, I can determine what direction the wheels are spinning in. And this is ultimately what I use to dictate the movement of the rover itself. So let's say we're just following the line and it's going straight. That means the middle sensor, or sensor B, would be triggered. So that would mean we'd want to move both wheels forward. And empirically, I kind of figured out that at full speed, it was going a little bit too fast. So I decided to cut that in half with the PWM duty cycle of 50% when it's moving forward. So that's both of the wheels on either side are moving forward. Then if sensor C is triggered, then we would want to move the left wheel forward and the right wheel backward. And to accomplish this, it needs a little bit more power to power through those turns. And so I give it 100% speed or just a full duty cycle. And then similarly, with sensor A, we'd want to move the right wheel forward and the left wheel backwards and also give it 100% speed. So some of the obstacles I ran into, first off, I had issues with the motor driver connections, and I was able to fix that just by kind of angling the pins accordingly, as you can see here, such that it's kind of forced to have these connections. I didn't want to do any soldering, so this was kind of a good way to bypass that. But on initial testing, I found that not all of the connections were perfectly routed through the motor driver as I had it initially set. So this is just kind of a method to ensure that. Other problems that I had was the battery power to move the entire chassis. As I said, we needed a 100% duty cycle to power through those turns because it just requires a little bit more power to accomplish that, and it wasn't working with the 50% duty cycle that I had set earlier. So that took a little bit of testing, but I was able to figure that out. And then lastly, I'm a little bit ashamed of this, but I learned that the AAA battery packs actually have an on-off switch, and it took me a long time to figure out that they do exist and that they were switched to off, and that would have helped me out a lot when I was trying to debug what was going on. So from that lesson, I basically just learned that it's really important to understand your hardware fully before integrating them into your project. So let's see this in action. And there you have it. One more video. Let's see. Here we go. So yeah, so as you can see, as it moves over the line and other sensors detect that those sensors are over the line, then it changes the wheel direction accordingly and is able to follow the line successfully. So like I mentioned, I think one of the things, actually I didn't mention this. So one of the things that would be beneficial for the for future improvements would be, further development of the chassis. Because this is more of a proof of concept, I think it would be much better to actually physically implement the wiring, maybe develop a PCB board, and actually just have a chassis that looks a little bit nicer, maybe with larger wheels in comparison to the size of the chassis, such that the back end of the chassis doesn't have to be dragged around at every turn. And that would also require a lot less power going into it, so I wouldn't have to do as much debugging with that, or troubleshooting rather. And then lastly, I think it would be probably more appropriate to have the PWM signals for each motor scaled individually, such that the motor on the inside of the turn would probably be turning at a lower rate and not just backwards, but maybe just at a slower speed. That would avoid some of the problems with skidding in general, and I think it would probably just make for smoother motion. Thank you, and hope you all had a good semester and have a good break going forward.